In small networks, routes can sometimes be entered manually. But as networks grow, manual configuration becomes difficult to maintain, especially when links change, devices fail, or topology expands. Routing protocols automate the exchange of reachability information so routers can learn paths dynamically. A routing protocol does not forward packets directly. Instead, it distributes information that helps routers build their routing tables. From there, the best routes are selected and installed for forwarding. This distinction is important because it reminds us that routing protocols serve the control plane, while packet movement remains a data plane task. In practice, different routing approaches exist for different needs. We begin by comparing static and provide a final routing summary before we move into MPLS and VPN services. A static route is configured manually by an administrator. It specifies a destination prefix and a next hop or outgoing interface. Static routes are simple, predictable, and useful in stable or small environments. They are also commonly used for default routes, temporary workarounds, or carefully controlled connectivity. Dynamic routing uses protocols that allow routers to exchange reachability information automatically. This makes networks more adaptable. If a path changes, the protocol can often learn and advertise a new one without requiring manual updates to every device. Dynamic routing is better suited to environments with multiple routers, alternate paths, and regular change. Neither method is universally better. Static routing offers simplicity and control. Dynamic routing offers scalability and responsiveness. Many real networks use both. To understand dynamic routing more clearly, we next look at two major families: distance vector and link state. Distance vector protocols share route information based on distance and direction, conceptually telling neighbors, "Here is what I can reach, and here is the cost to get there." Routers using this model learn from their neighbors' advertisements and build their understanding progressively. Traditional examples include RIP, while some protocols combine or extend these ideas. Link state protocols work differently. Each router describes the state of its directly connected links and shares that information so all routers in an area can build a consistent topology database. Each router then runs its own shortest path calculation to determine the best routes. OSPF is a well-known link state protocol. In general, link state protocols provide better scalability and topology awareness than older distance vector designs, though they also require more processing resources. Next, we explore OSPF in more detail. Open Shortest Path First, or OSPF, is a link state routing protocol used inside an autonomous system. Routers running OSPF form neighbor adjacencies, exchange link state information, and build a shared view of network topology within an area. Each router then runs the shortest path first algorithm to compute the best paths. OSPF uses cost as its path selection metric. Lower total cost is preferred. It supports hierarchical design through areas, which helps control scale and organize topology. Area 0 serves as the backbone, and other areas connect to it in standard designs. A practical example would be an enterprise WAN where branch routers connect to regional hubs, and all of them participate in OSPF to share internal reachability. If a branch's primary link fails, OSPF can reconverge and direct traffic through an alternate path if one exists. For internal routing, OSPF is common and powerful. But when routes must be exchanged between different administrative domains or under explicit policy control, BGP becomes central. Border Gateway Protocol, or BGP, is the primary routing protocol used to exchange routes between autonomous systems and is also widely used within large service provider and data center environments for scalable policy-based routing. Unlike OSPF, which emphasizes shortest path calculation within a topology, BGP emphasizes controlled path selection based on attributes and policy. BGP allows networks to decide not just whether a path exists, but which path should be preferred according to business, engineering, or administrative rules. Attributes such as AS path, local preference, and MED influence decisions, depending on implementation context and policy design. For example, a provider connected to two upstream peers may prefer one for outbound internet traffic while keeping the other as backup. That choice is not simply about shortest distance. It is about policy. This makes BGP highly flexible but also more conceptually demanding. To use either OSPF or BGP effectively, we need to understand how a router chooses one route over another. A router may learn multiple routes to the same destination from different sources. It must therefore select a best route. The exact process varies by platform and protocol, but in general, route selection considers factors such as source preference, metric, protocol-specific attributes, and route specificity. One important principle is that route source matters. A directly connected route is often highly trusted for its local network. A static route may be preferred over some dynamic routes, depending on administrative preference values. Within a protocol, metrics or attributes then influence which path is chosen. And as we discussed earlier, if multiple installed routes could match a packet, longest prefix match determines actual forwarding. This layered decision process explains why troubleshooting route selection requires careful attention. You may need to ask, was the route learned? Was it preferred over alternatives? Was it installed into forwarding? Understanding that chain prepares us for a final routing summary before we move into MPLS and VPN services. Routing protocols allow routers to learn network reachability at scale. Static routing provides simplicity and control where manual configuration is acceptable. Dynamic routing provides adaptability and scalability when topology or path choice becomes more complex. Among dynamic approaches, distance vector and link state represent different ways to share and compute reachability. OSPF is a widely used link state protocol for internal routing. BGP is the dominant protocol for policy-driven route exchange across domains and in large-scale architectures. In every case, the router must evaluate available routes and choose the best one for installation and forwarding. With that foundation, we can now examine technologies that extend routing and service delivery in provider-style networks, MPLS and VPN services.